All right. So am I good to go here? All right. Just had to check with our AV people who, by the way, let's give them a round of applause. Every month they're here. Okay. So typically, I'm the one giving the introduction, and I guess we won't break with that tradition. I'm J.D. Armstrong. I'm the Maui Technology Education and Outreach Specialist here at the Institute for Astronomy. And this, one of the things I do is put these talks together. I also work with the community. A lot of people in the audience tonight that have helped out with star parties, things like that. So now I give the introduction for myself, and our speaker today is Dr. J.D. Armstrong. And his nefarious background is that he was born and raised in Salt Lake City, Utah. He had his bachelor's degree in physics from Westminster College there. It's a small school of about 2,000 people. I next ended up at Michigan State after a detour or two, and got his master's in physics, and he was specializing in nuclear theory, really interested in quantum chaos. While at Michigan State, he got his black belt in martial arts, and so when he starts talking about ninjas, he knows a little bit about what he's talking about, maybe just a very little. From Michigan State, he went to the University of Hawaii and received his doctorate in physics. Then he ended up over here working for the University of New Mexico, and when about a year later his group was hired by the Institute for Astronomy, he ended up with the Institute for Astronomy again. And so that's how I got here. Now you know. All right. So currently I work for the University of Hawaii Institute for Astronomy and also the Los Cumbres Observatory Global Telescope. And I have a laser pointer. If you've got one. Let me just check. Top button. Thank you. Oh, here's mine. I'll let you keep yours. The benefits of giving a talk to a scientifically literate audience is they always have the toys you want to play with. All right, let me get this microphone settled again. And so I also work for Los Cumbres Observatory Global Telescope, for those of you who are familiar with the Falks Telescope North on the summit. That's the company that owns and operates it. They send me part of my salary every year, or every month, or whatever. All right, a couple announcements. First of all, I hope that you will all be watching Jeopardy this Friday, because the Clue Crew visited here last year and filmed a bunch of clues up there, and there will be a category of Holyoke Law. So that'll be kind of cool. So tomorrow, noon, check your listings because I may have messed it up. And especially if you're not here in Hawaii, check your listings. I know in Michigan it was at another time. Yeah. Yeah, it was bumped for the basketball game. Yeah, usually it's on at 4 and 5, from 4 to 5. But tomorrow there's the basketball playoffs, and so they've moved it to noon. But check your listings. Okay? All right. Also, the next public talk will be on Friday, April 8th, 6:30 p.m. I'm not going to try to pronounce his name because I will probably mispronounce it. But he will be talking about the physics of music, or what do a tuba and a tsunami have in common. Very timely for our current events. Okay? So, I was going to talk to you guys about ninjas, right? Okay? And I actually, like I said, I have studied some of the modern art of ninjutsu. When I was a teenager, I bought some books by Stephen Hayes. Also took a few classes in the arts. And the original ninja were actually referred to as the shinobi. The term ninja is something that was derived that was a more westernized version of Europeans. You really were the ones that used the term ninja. And the reports of ninja date back to the 14th century. And these are, of course, the famous spies and assassins of feudal Japan, right? Okay, and then there are all these wonderful stories about ninjas and their powers, right? Everyone, thank you. I had to do that with my college classes a few times until they learned. All right? So, for example, ninjas could turn invisible. All right? They could walk on water. Well, I didn't say I was any good. I said I studied some of this. People said they could walk through walls. They were masters of infiltrating castles. They did a great deal of reconnaissance, so they became famous for walking through walls. They could turn into small animals, rats, birds, and they could levitate, just float right up in the air and cast magic spells. So all of you believe this, right? Yeah. Well, the truth about ninjas is that they were the special forces of feudal Japan. Okay, they started out as peasants who adapted their farm instruments for combat weapons and also tools for infiltrating castles. And then after a few centuries, they developed into sort of a new caste in Japan, and they would have families that the children would learn would learn the martial arts and the infiltration techniques from their parents. And they would start at a very early age, similar to the way the samurai were trained. The samurai were trained from, very early on to practice the martial arts and their honor code. The ninja, in later years, they started at the same ages, trained in martial arts, evasion, camouflage, things of that nature. Okay? And contrary to the modern belief, this was a more typical ninja outfit. It's the more modern ninja that wears the black gi with the mask that we're all used to. This is probably a much more accurate historical image. Okay? So we're also going to talk about asteroids. Asteroids are the leftover material from when the solar system formed, the stuff that didn't coalesce into planets. So it's sort of the peasants of the solar system. All right? Generally, it's made of silicates and metals. The more volatile things of water and gases have boiled off. And for rocks that most of it hasn't boiled off, we call those comets. So comets are, when I was growing up, comets were these snowballs, these balls of ice. And asteroids were these balls of rock. Now, asteroids are chunks of rock with some snow in it, and they're snowy dirt balls. And comets are dirty snowballs. So they're very similar things. And the comets are generally from what's called the Kuiper belt. That's a belt of objects that orbit the sun out about the distance of Pluto and a little beyond. So Pluto is considered to be a Kuiper belt object. I'm not going to debate with you whether or not it's a planet. We all have our opinions. All right? So these are some of the major areas of asteroids. You have the Trojan asteroids over here. I believe it's Trojan, if I'm wrong. Okay, thank you. Over in the Lagrange points with Jupiter, the main belt. But the ones we're most interested in are Earth-crossing asteroids, things that are close into us, because those are the ones that can hit us. Okay? asteroids are assassins. There's an estimate that about 100 tons of material falls on the Earth every day. Now, you'll hear the estimate of how much material varies widely because it's mostly small stuff. Every time you see a shooting star, that's a grain of dust entering the atmosphere. And that's mostly what lands on us. But every now and then something bigger hits us. Say maybe the size of a baseball. Or every couple hundred years, something 100 meters across will hit us. Something the size of a football field. This is a picture from the aftermath of the Tunguska strike in Russia. The blast radius for this was about 17 miles. And it was believed to be caused by a meteorite, or a meteor, that was less than 100 meters in diameter. We could get hit by these every 100 years, 200 years, somewhere in that range, every few hundred years. Now, Siberia is very isolated. There was only one person reported missing, and to my knowledge, there has never been someone there's no record of anyone ever being killed by a meteor strike. But imagine this happening 8 hours earlier. Would have happened 8 hours difference in time zone over North America or over Europe. This could have been a very serious event. The predictions are that we have about the same chance of dying in a meteor strike as we do in an airline accident. And so we think it's important to watch this. It's not, don't be afraid of it. I'm not going to be a gloom and doom prophet. I don't believe in 2012. But this is something we should look out for because we can prevent it if we see it far enough in advance. Okay? So there's a 1% chance the Earth will be struck by, say, a 300-meter near-Earth object in the next century. That was a prediction. That was a calculation done by Dr. Dave Jewett. And there have been several times where the Earth's been hit by bigger objects that have caused mass extinctions. The dinosaurs. All right. And so the biggest threat from our assassins, from these solar system ninjas, are when the orbit crosses the Earth's, when they're a little bit more elliptical and they go in and out. Because then the asteroid has repeated chances to hit us. Okay, well, I missed this time. Well, I'm going a little slower, so next time the Earth comes along, I'm going to hit it. Okay? And so right here, when we have these crossings, maybe it doesn't happen the first time, but the timings are off enough that eventually we can get hit. That's what we're worried about. So, the legends of the asteroid. I'm not going to get into this, guys. I don't want to go into the 2012 hype. If this were December of 2010, I would say that there is no more chance that the world will end in 2012 than 2011. Okay? I just don't see anything that tells me that is going to happen. And that is a debate that I'll get into you with. All right? So, you ready? Asteroid, Ninja Asteroid, super secret, number 1. Dark colors make you hard to detect. So this is an object that was given to me by Mary Kadoka, and it was provided to her from NASA. This is a model of Comet 9P Tempel 1. They apparently spent a fairly good deal of money creating these models and made them as accurate as possible. So in addition to being a great paperweight, it actually is useful for demonstrations such as this. This is not a very bright colored object, is it? Okay, it's not reflecting a lot of light. This is actually fairly bright for an asteroid. So fairly dark objects, and that makes them more difficult to see. Right? If we want to see something, we have to see the light from it. Almost all astronomy is based off the light that comes to us from other objects. Radio waves are included in light, but here's an object that doesn't reflect a lot of light and doesn't generate its own light. Very difficult to detect. So let's look at what I mean by that. Albedo is the fraction of light which is reflected by the surface. And this is a graph that I found online showing, with distance from the Earth, how much light is reflected. And this is an albedo of 0.1. So something like a tenth of the light is actually reflected by the surface, is actually scattered back. But then it's also scattered in all directions, so it makes it even more difficult for us to see it. These are very dark objects. Okay? Ninja Asteroid Super Secret number 2. Stay out of the light. Okay? So, when I was practicing my ninja arts and playing the game called Steal the Flashlight, if there was an area that was lit, you'd move across it very quickly. So if someone is in their house and turns on a light, you're going to want to move quickly in order to get across that area without being seen. And then you can move more slowly where it's dark. And asteroids seem to do this as well. So we're looking at these near-Earth asteroids, these Earth crossers. Those are the real ninjas. The main belt asteroids, not so worried about those. Okay? So let's follow with the Earth as the Earth is rotating around, and here's our asteroid. It kind of looks similar to the moon because the sun is shining, in this picture, the sun is shining up from below. Okay? We see the side that is closest to us. So in this case, let's pretend this is the moon. What phase would the moon be? Be full moon. All of it's lit up. And so would this be easier or harder to detect? Easier. But it's relative to what we're seeing, this play right there, it's actually moving faster than over here. You can see that the angular speed of this object gets slower as it moves over here. But what's the phase of the moon when it's there? Yeah, it's like third quarter. It's only half lit. And so when it's over here, it's moving more slowly. Here, it's easier to see, but it doesn't spend much time there. And so we have to be fairly lucky to align the telescope and see it at that point. Over here, we can point for a long time, but it's not as bright, and so it's difficult to detect. You'll have more asteroids in the same field of view, but they're harder to see. So, Ninja Asteroid Super Secret number 3. Be unpredictable. All right? So, this is a picture of what's called retrograde motion of Mars. We have a composite image of the same area of the sky, and that was taken over a period of 9 days. And Mars seems to be wandering along, moving along nice and orderly, and then it changes its mind and wanders back, and then it wanders around this way again. Asteroids will undergo a similar retrograde motion. And let me explain how this works. So, in the case of Mars, which is this outer ring here, and the sun here. So we start here. The Earth is here, Mars is here. And we look out at Mars, and we see it lining up with this spot in the sky. Okay, is that clear to everyone? Right? Okay, good. Mars moves along, and Earth moves along, And so a little while later, Mars appears to be at this part of the sky. Everyone following so far? All right. So now Mars moves another step. Earth moves another step. Now Mars appears to be over in this area of the sky. Well, this next step, Earth starts overtaking Mars. All right? Because the Earth is traveling faster, but it's not traveling in the same direction. So now we see Mars in this position. It was going in this direction. Now it's coming back. Okay, a little while later, we see it's gone down, and now it's coming back up again in this position, and then we see it going back across the sky in the same direction again. Okay, does everyone follow that? If so, I'm impressed. I had a hard time explaining this to people before. Okay, but basically, asteroids will move about on the sky sometimes erratically. Most generally, they'll move in arcs. Okay, so Ninja Asteroid, super secret, number 4. Blend in. Okay, so here we have a picture of a tree. And then you start looking more carefully, and you realize that there is a person here. Can everyone see the person? Okay, you see this right here? And then here, and then here. You can see that this is the tree, but right there is the person. Okay? I was not very good at at blending in and hiding. Yeah, that's the jacaranda outside King K. Nice. I wanted to take a picture of a purple tree for my niece. Okay, so asteroids do this too. They look very similar to stars. Here's a picture. Can anyone tell me where the asteroid is in that picture? Where?
I don't know.
Exactly. You don't know. Can you tell me?
Over there.
Here, push this button and point. We'll see if you get it right.
Over there.
That one? Nope.
Over
Nope. Okay. It's the white one. All of these things are stars. These are all stars. And from a single image, they all look the same. The reason is stars are smaller than 1 pixel in our detector, and so are asteroids. Imagine we're looking for 100-meter objects, and Congress has said we want to find 90% of all objects that are 1 meter in diameter or larger by the year 2020. Good luck. Yeah, thank you. We need it. All right? So, it's smaller than a single pixel. And we're looking at things that are farther away than the moon. Can you imagine trying to see a football field at a distance greater than the moon? Good luck is the right sentiment. Okay? But we can outsmart ninjas. We can outsmart the ninja asteroids. Okay? This is a project that was done. This was part of a student over at King K. Kaileke, his senior project. These two images were taken at the same time. One was taken in Hawaii and one was taken in Utah by an amateur astronomer out there by the name of Patrick Wiggins. He's one of the NASA ambassadors to the solar system, or at least he was at one point. I think he still is. But Patrick and I were working with the student, and we tried 4 times to get this before we finally got 2 images of the same target. And you can see this dot here is in a different position. Okay? That's called parallax. It's the same method by which one of the methods we perceive distance with our eyes. Each eye sees the object at a little different angle because it's close in. by measuring the distance, or the parallax from these two images, we can tell how far away that object is. This one happened to be about 60% of the distance between the Earth and the Sun, so 0.6 astronomical units. All right? Questions so far? Everyone doing good? All right. So, how do we look for asteroids? Why are we always putting the telescopes on the summits of Haleakala and Mauna Kea? They're the best sites in the world. It's difficult to find these objects, and so we need the best site in the world in order to find them. And that's the very real reason why. And light pollution is another problem. Okay, if you have what?
I got a question that came up when you're ready.
Oh, okay. Let me go with the question. We'll pause right here.
What was the magnification on the parallax images?
On those parallax images, the 1 pixel in the image labeled UT is about a quarter arc second. And so I can't tell you right off without counting what the magnification would be from there.
Thank you.
Okay? All right.
Say thank you.
You're welcome. All right. I think that's the first really good question we've had from cyberspace. That's great. All right, so this is why we have these telescopes up there. The Pan-STARRS Observatory on the left was built for the purpose of looking for these near-Earth objects, and it spends only about 10% of its time doing that, and the rest of the time doing other science. It's really an amazing project, but we're going to talk about the asteroids. So it spends about 10% of its time looking for asteroids. Problem is, it's a survey telescope. It'll scan through and try to observe the entire sky. So it looks here, looks here, looks here, looks here. Then it'll jump back and cover that same spot in the sky 4 times during a night. Then the next night, it has another area of the sky that it's looking at. If an asteroid's found, then these guys don't go and find it again. They don't go and follow up on that asteroid, and so we don't know where it is. That is a good place to use the Falks telescope, which is a similar sized telescope. It can go about as deep as Pan-STARRS. In other words, it can see objects that are about the same faintness, about the same brightness or faintness. But this is a telescope that is for use by students, okay, or learners of all ages. This is not mainly to be used by scientists, okay? That's what the IFA promised would be done with the time for Hawaii when it was built, and that's what we're doing today. So, students can use the Falks to do observations of that. There's a program that we are working on right now, follow-up positions for Pan-STARRS, and I'm going to give you a demonstration of this. Okay? What we'll do is we measure the position of an asteroid. Okay? Then we have an idea of how it's moving, and we predict the position. We make new observation, we refine the orbit, and repeat. Any teachers in the audience here? Okay. Does that sound similar to something called the scientific method? Yeah, last time you checked. Okay. Another nice thing. We're going to go into equation of a line, unit conversion. Any of these sound like state of Hawaii teaching standards? Yeah, exactly. Okay, so we've got the scientific process using models to make predictions, equation of a line, unit conversion. This begins March 27th, actually 28th, I apologize. Baldwin High and Maui High have already participated in this. Kamehameha schools in Hilo will be participating this coming round, beginning in March. And if there are other schools that want to participate, You know where to find me. All right, so let's go ahead and do a demonstration. I'm too lazy, so I brought some helpers. Let me introduce Kailens. He is a student at Baldwin High School, and his senior project was on asteroids, or actually, sorry, I got that wrong. Let me introduce Anthony, who is a student here on Maui, born and raised. Come on up. What Anthony is going to do is he's going to demonstrate, using data from pan-stars, how we actually measure the positions of asteroids. So you just want to go ahead and click on that. And the first thing he's going to want to do is make sure that he has the correct configuration files. And so he'll be clicking on the little wrench there. Yeah, there we go. And he's going to open up his configuration file. In this case, we're using pan-stars 1. Okay, and open that. Okay. So just click on OK. All right. Then he goes ahead and opens the images. These are provided by pan-stars for the schools. Okay. And there we go. Was 38 the good one? Okay. And so let's make this audience participation. Does that sound like fun? Okay. Keep going. I'll distract you in a minute. Okay. So it takes a moment to load the images. Notice that this little block comes up. He just clicks OK. It's just confirming that the coordinates and time are correct in the FITS headers. Okay. So then he comes up to the top here, and he clicked on this green button, which tells the program. Did you do the right thing? Oh, okay. You went to blink?
Yeah.
Okay. No problem. So he didn't do anything wrong. It's a little more efficient to go over to the green button first. What he did is he went over to blink. And so this will show us the images kind of like a movie. It'll play through them repeatedly, and we'll be able to look for objects that move, such as asteroids. Okay? So I'm going to go ahead and close that. Yeah. And so go ahead and click on the green button here. Yeah, there you go. Okay. And then this is another little window that just pops up. Obviously, you can see that Anthony knows what he's doing. All right? Okay. The computer right now is looking at all these black spots. This is a negative image of the sky. It's looking at all these black spots, and it knows that most of them are stars. So it's lining them up in all the different images. And in a moment, it'll download some data from the internet, from I believe the Minor Planet Center, and it will compare to star catalogs. So then it will know every position on the image. It'll know the exact right ascension and declination. Okay, the stars give him a reference frame, and he's going to be looking at using the stars to establish that reference frame. There we go. Now hold on for a second. Sometimes this comes up, which it says reference star match error. And basically what's probably causing this is some of the glitches in the images. But if we look, all the little blue circles tend to line up with something that looks like it should be a star and should be there. So we're going to go ahead and say present possibly erroneous match, and go ahead and click OK. All right. So go ahead and hit reject on that. All right, he's going to move that out of the way so that make it easy. And now he's going to go ahead and blink the images. Blink the images first. Anthony, blink the images first. Okay, there you go. Now go ahead and zoom in and scale your window. Okay, and so here's the audience participation part. I want everyone to kind of watch and see if you can see an asteroid. If you see something that you think might be an asteroid, I want you to applaud or say something or wave. I don't know. So something that you might think would be an asteroid. And Anthony is going to move around the image every now and then. And as soon as somebody sees something, we'll stop and take a look at it. These are real images, real data that was not touched until some students at Baldwin High School looked at them. Okay. All right. There it is. Okay. So we found that. So go ahead and keep it blinking for a minute, if you would, please. Okay. So Anthony went up to these controls up on the right-hand side and clicked the stop. But hold on. So let's go ahead and move over so that that's in the center of the. Go ahead and play. Hit play. So go ahead and move that into the center of the field of view. So slide around until we've got it fairly close to the center, and then slide down a little bit. Okay. So we can see this asteroid in all 4 positions, or what looks like an asteroid. If it's an asteroid, on a time scale of about an hour, it should move in a fairly straight line. And so we'll get to that in just a minute. What we'll do now is Anthony's going to go ahead and mark the image, each image. Go ahead and get one on that. So first he hits the stop button, which is that red button near the top. And then he just clicks on the asteroid. If he needs to check where the position is, he can hit the 2 black arrows to go 1 frame forward and 1 frame back, just to look for anything that is there. Now hold on at this point. So after clicking on the asteroid, there's a few things, this window will pop up. There are a few things you want to look at. The full width half max. Okay, that should be somewhere around 0.8 arc seconds. If there are any amateur astronomers on the mainland who are watching right now, they're drooling at 0.7 arc seconds, I guarantee. That is an incredible sight. That's where Pan-STARRS is, and that's an actual measurement of the resolution of the sky. It's basically saying how small of a feature on the sky we can actually see. Okay? Sometimes you'll click things that have way too big a full width of half max or way too small of one, and then you know that's the first sign it's not an asteroid. Then Anthony gives it a name in the little box there, in the little puka. And what is typically done is you get the first 2 letters of your last name followed by the number of asteroid detection. So if it's your first asteroid detection, you put 0001. Notice he's put 0002. Okay? So go ahead and hit it. And then at that point, he goes ahead and hits accept. All right? And he'll go to the next frame. Black arrows at the top are what he uses. And then if he loses the asteroid, just clicks, blinks between 2 frames, just steps. And then go ahead. Just keep going at this point. And then he just repeats the process. This is the same asteroid in the second image as in the first image, so it gets the same name. Okay? And each time, the full width half max is about 0.7, 0.8 arc seconds. All right. There we go. All right? And when he's got all 4 of the images marked, then he plays just to check and make sure that they're all aligned. All right? And now what he can do from this program is he can get the Minor Planet Center report. And there are only minor changes that you have to make to this Minor Planet Center report. Okay? So he's going to copy this now and paste this into a notepad so that we can allow Kailens to come and predict where the asteroid is going to be on another day and show you how that is done. Okay? And save it, please.
What was the time frame on those 4 shots?
It was a span of about an hour.
Okay.
And these are actually images from December of last year. So our predictions are going to be no good tonight because the uncertainty in the positions is too high. And even if you had fairly exact measurements of the positions over an hour, there's different types of orbits that the asteroid could have, and they would all look similar over 1 hour. And so we don't know the orbit well enough. That's why we have to observe it. Once we observe it, we have to predict where it's going to be and observe it again within a few days, typically. And if we don't observe it within a few days, we lose it. For a near-Earth object, 2 days is sort of the most I would even try. And so what Kailens going to do now is he's going to take this, just take these straight into and put them into a spreadsheet that we've put together. And he made his own version of this. He's using mine right now. But he's just going to paste this in here. And he gets all these numbers. So it gives the time, the year, the day, the date, and then the right ascension, which is like the longitude in the sky, and the declination, which is like the latitude in the sky. So these are the coordinates of where it is in the sky. And he's just choosing a fixed width and making sure that everything's good. Go ahead. Okay? So all he's done is posted these numbers in here. So let me go ahead and thank you. That's perfect. So hold it there for a minute. So this is the first column is the name of the asteroid. Second column is the year. Third is the month. Fourth column, the D column, is the day. And notice there's a fraction of a day, so 0.39 days. What would 0.5 days be? 0.5 days. Half of a day is how many hours? 12 hours. So 0.39 hours, you can figure out, or 0.39 days, you can figure out how many hours, minutes, and seconds that is. Okay? There's our unit conversion right there. Okay? Then we go into the right ascension, which is in E, F, and G. E is the hours of right ascension, F's the minutes, and then G is the seconds, and then the declination. Okay? And then column K is the magnitude, how bright, a measure of how bright it is, and L is the telescope that you used. And so if you'll scroll over to the right a little bit, please. Notice that these points are in a fairly straight line. What we have plotted here is on the y-axis, on the x-axis, on the horizontal axis, is the date. So it's I just have the day in here, so 5, and it goes over about a period of an hour. And then on the vertical axis, on the first graph, I have the right ascension. And I've converted the right ascension, the hours, minutes, and seconds, all into seconds. All right? That way we can very easily we get the coefficients for this line. So we have a slope of minus 4.14. There's our velocity, another key concept in science, right? And just some offset. All right? And then the next graph over is the declination. And so that, again, it should be a straight line. If both of these are a straight line, then it's moving in a straight line in the sky. All right? And so we can take these coefficients, and Kailens will have to type those in down here. Type those in right there. You see the, yeah, so type the slope in. So minus. Sorry, we actually rehearsed a little bit, and now I'm throwing him for a curve because we forgot to do this. But obviously, he's done this before. Kailens got to the point that I would give him the observations from pan-stars, the coordinates from pan-stars, and he would just go ahead and do it. I could have walked out the door, let him go ahead and predict the positions, point the telescope, and take the images. He knew what he was doing. All right, so he's basically just entered these in here because those are the cells that are used to reference for making a prediction. Now, what we're doing is we have this line. We're just projecting it forward into the future. And that'll give us a fairly good approximation of where that asteroid should be. So, Kailens, would you go ahead and show them where that is up here? All right? And so he can go ahead and change the date around, and notice that these next three numbers will change. That's the right ascension and declination that's predicted. But again, this was back in December. By March, it's done. It's somewhere else in the sky. All right? All right? So go ahead and there's a more advanced way of doing this, a program called Find Orb. And so if you'll go ahead and show them Find Orb. Did we close it? We closed it. Okay, so yeah, documents, job, yeah, Falks, and then should be Find Orb, and then you know what to do from there, right? Okay, again, he knows what he's doing once I find it for him, because I have my computer as big a mess as my office. So you're going to just go ahead and yeah, look for the, scroll down. Yeah, so this is the file that, that Anthony just made. These are the actual measurements that Anthony just made. And Kailens going to just go in here. Once you open up this program, you get the coordinates that you've already measured. You click once on this, and then you ask it for the ephemeris. There are a couple little pieces of information you give it. And he knows exactly what he's doing. And so there's his predictions for where this asteroid was. And I'll bet that if we went on to the Minor Planet Center and that asteroid were listed, then I'll bet these coordinates are fairly close to correct for where it should be today. Yeah?
For a 1 hour observation in December, you're going to predict 4 months forward?
No. No.
You lost me.
No. Okay. So let's say that this is a known asteroid. Yeah. And we were looking, you know, for a couple days later. Then we could go and check on the Minor Planet Center. We can only predict from 1 hour about a couple of days, maybe up to a week, depending on what type of asteroid. If it's any longer than that, it's really dicey. You have to have a lot of luck in order to get it, even with the Find Orb program. Even with the most advanced techniques, you'd have to have a lot of luck.
How long would you have to observe it if you would actually want to be able to predict it for a month or so?
For a month, I would want to have probably at least observations spanning a couple days, a couple, 3 days. Again, it depends on what type of asteroid you're looking at. If it's a main belt asteroid from an hour time span, you're probably still good for a week using the Falks telescope with 10 arc minutes field of view. Okay, that's a main belt. If it's a near-Earth asteroid, there's no way you'll catch it for a week. You're lucky if you catch it the next day. All right? To go out to a month, give me a few days. To go out to next year, you want to have it over at least a month, preferably about 2 months that you have observed this. Then to name an asteroid, you have to see it at I believe 7 oppositions. You have to see it several times watch it for several years. Okay? Yeah.
So is there any way to tell from looking at something like over 4 shots like that what it is? If it's a near-Earth object?
If it's a near-Earth, there are some indications. Okay? If it's moving very fast, it's probably a near-Earth object. But that doesn't always work. And Pan-STARRS every now and then has an observation that they believe is a near-Earth object, and the Minor Planet Center, who's at Harvard and is sort of the accepted authority, says, well, we don't agree. And it's a very friendly disagreement. And so they say, well, we're going to try to catch it. And they say, all right, good luck, let us know. And, you know. But here's the thing. You remember the image I took that I showed you with the parallax, the image from Utah and from Hawaii. Okay? If it's a near-Earth asteroid, two images that far apart, you can tell how far it is from Earth fairly accurately. And then you could immediately say that, yes, it is a near-Earth asteroid, or no, it's not. All right?
Define near. How near is near?
I don't know.
I was looking for a definitive 16,425 and a quarter miles.
Yeah, it's the Pluto argument again. I don't know where the range, what the range they define to be a near-Earth object. And I don't even know what I would consider to be a near-Earth object, to be honest. If it's in closer than the moon, if at some point it passes within the moon, radius of the moon, it's definitely a near-Earth object.
It's too close.
Yeah.
Close.
It's way too close. That's, you know.
Might be a PHO.
Yes. A PHO is a potentially hazard object. Potentially hazardous object. And, all right. So, you good? All right. Any questions for either one of my assistants? How about
Did you guys train here for?
Callan? How long did you train here?
Maybe like 2 or 3 months.
So about 2 or 3 months of putting up with me, if you can put up with that. You can be doing this too. And Anthony, how long have you been working with me?
I don't know, maybe a few months just on and off.
So a total of a few months on and off. Anthony, I met him, it was February of last year when Dr. Filipenko came and spoke here. So,
Kudos from the live audience.
so kudos from the live audience. Thank you very much. Yes, let's give these guys a big hand. And I'm noticing quite a few students that I've been working with, not just asteroid students. So, yeah, I hope you guys are not feeling left out, but tonight's an asteroid night. So let's go back to the presentation here. We're just about coming to the end, so you won't have to hear me drone on for much longer. So, the demonstration. One of the projects that is interesting and sort of related to this is, okay, well, imagine that we're going to get hit by an asteroid. We want to be able to do something about it, and before we can do something about it, we need to know what it's made of. All right, I already see people in the audience getting ready for what will be my next question. One way we can learn a little bit about their composition and collisional history is by looking at the rotation rates. And so we have here 4 asteroids, 4 simulated asteroids. And as the asteroid tumbles, how bright it is will change a little bit. And this is a good example of how that happens. So on the left, I have these 4 asteroid images, these animated images. And on the right, we have how bright the asteroid is as a function of time. So the horizontal axis is time. The vertical axis is how bright it is. Brighter is up towards the top. Now, your challenge, and I know that a few of you already know the answers. You folks keep quiet. All right? What we want to do is we want to match these curves with these asteroids. Does anyone want to hazard a guess? Okay. Which one do you want to match?
Number 4.
Number 4, and which one does it match up with here? That one?
No, that one. No.
Push the button. So the upper right. So number 4 is not the upper right, but that's a good job. We got to applaud for courage, and I see where you're coming with that. You're not too far off. Okay. So, does anyone else have... Let's try to match one of the easy ones. Let's try to match number 3. Who wants to give me a guess for which one's number 3? Which one? Again, I'm going to have you. So, that's very close. That's correct. So the top left is image number 3. Okay? So what's happening is right here it's constant, constant, constant. Now when they go behind one goes behind the other, the amount of light drops because you're only seeing one of the two of them. All right, so number 3. Well, once we've got a good example like that, the rest should be a little bit easier. Can you tell me which one is number 2 now? Who can?
Top right.
Top right. Okay, good. All right, and what about number 1? This is the next hardest. Bottom right. It's nice and regular the way it's going up and down. And then number 4 is obviously the bottom left. Kind of irregular. It's a spherical asteroid, but it's got little discolorations on its surface. And there's actually a student over on Oahu who is doing a science fair project on this, is going to the state level with data from our very own Falks telescope. Shall we give the telescope a big hand? Okay, so before I go too much farther, I just want to make sure that I clear up one misconception, and that's about what my work is. Okay, I may have given you the impression that I work with asteroids. I don't work with asteroids. I've pulled together the work of several students, like Anthony, Kailens, and other students around Maui and Hawaii. Okay, so this asteroid, the stuff that I've been talking about on asteroids, that's not my work. This is my work. These are all students that I've worked with. Okay, I went a little overboard last night. This is also just a small fraction of the students that I've worked with. Michael, that was the student that, yeah, okay, there we go. So, domo arigato gozaimashita. Thank you very much. Any questions? Yes.
Say we know that there's an asteroid nearby. What do we do if we have to
Repeat the question.
Okay, so the question is, suppose there's an asteroid that is nearby. What can we do to prevent it from hitting us? Depends on how long we have. If we have a year, well, we brace for impact. If we have 20 years, we can send a spacecraft up and divert it. Now, you've seen the movie Deep Impact where they go and they put the bomb on it. Bad idea. Don't. Yeah, I mean, do you want to get hit by a rifle or a shotgun? That's your question there. It's just a bad idea. What you want to do is you want to divert it. If you have long enough to divert it, all you have to do is prevent the Earth and the asteroid from being in the same place at the same time, right? If you're coming to an intersection, this is the problem. This is not a problem. This is not a problem, as long as it's not in the same place at the same time as the Earth. And so we only need to move it about the distance of the Earth. What they will do is they'll put a heavy spacecraft near it, and then the gravity from that spacecraft, the asteroid will start to fall in to the spacecraft. Spacecraft will fall into the asteroid as well, but then you'd use the thrusters on the spacecraft to kind of back it off. And so you very, very slowly tug the asteroid out of the way, change its orbit just enough that it misses us. We've got a
So nickel-iron asteroids are less plentiful than we used to think?
So nickel-iron asteroids are less plentiful than we used to think. I don't know, to be honest. I know that most of them are silicates. Okay. Yes.
Do you know of any hardware the government has or has under development presently to handle such an event?
Do I know of any hardware that the government has under development to handle such an event?
Once the killer...
So once a killer asteroid is detected, does the government have any hardware that they're currently developing? Very early stages, yeah. I think that there are some projects. For a while, they were just saying, "Oh, let's go nuke it," and then we explained to them, "No, let's not do that." Another idea that has been proposed, and really I think what it mostly is small models that they've developed. Another idea that they've proposed is put a lens there, you heat up one side of the asteroid, and it outgasses and changes the orbit. So
That would be very much like a standoff nuclear event, maybe 10 kilometers or so. You could cut the outgas there from the prompt X-rays and give it a little tug.
right, so a standoff nuclear event where you have a nuclear device near the asteroid, maybe that would work. But you wouldn't want to do that if it were, say, a rubble pile. So if it's a pile of gravel in space and you have this nuclear event, it'll just kind of take off the front pieces instead of pushing the whole asteroid. If it's a monolith, in other words, a solid rock, then it's a great idea to do that. Most asteroids we're beginning to think are not monoliths. They're not a solid pile of solid rock. They're piles of rubble. So,
For instance, the big
Yeah.
one in Russia, they've never found any pieces of it, right?
oh yeah, I was just talking about it. Tunguska, thank you. Brain cramp. Yeah, Tunguska, they never found any pieces. Part of that, though, could be that it was during World War I. People were busy then. And the other reason is that they think it just really disintegrated in the atmosphere.
Yeah, I was
Kevin?
going to say they thought it was a bolide that exploded above the atmosphere.
Yeah.
That's why it flattened all the
Yeah. That was roughly the equivalent of between a 10 and 20 megaton nuclear event. So something like 1,000 times Hiroshima. Yeah.
How many of these are now sort of known? I mean, I remember seeing a thing on, I think it was here, but where a few years ago we thought there was only a few, and there's more and more every year that they see.
Yeah.
You guys see, I guess. How many are we looking at?
Okay. So the question is, how many of these are known? A few years ago, it seemed like there were only a few of them, and now we're discovering more and more, and it's beginning to look like that maybe there's a lot of them. So when I go to the Minor Planet Center and I specify how many, how bright an object I want to look for, I usually go to about 22nd magnitude. I don't know what size that is, but that's fairly faint. And they talk about 500,000 objects. Okay. As far as near-Earth objects, we don't know. Any estimates? Kevin, do you have any ideas? 20,000 near-Earth objects. Okay. And then, so there are a lot of them out there. What is really scary, though, is we are beginning to think that maybe we don't know where most of them are, up to the size of a football field. A football field is big enough to cause some severe damage. Tunguska was, they estimate, between 50 and 100 meters across. Football field is, say, 100 meters across. So, yeah, we don't know how many there are. And we keep adjusting the estimates up. That's right. Questions? From our audience?
Are nickel-iron asteroids the remnants of a larger body's iron core?
Are nickel-iron asteroids the remnants of a larger body's core? Yes. A star's core. So the nickel and iron were all formed in the core of a star that went supernova, that blew up. And in fact, so is carbon and everything else. But whether or not it came out as a big chunk, I don't know. I think there are some indications that that's the case, because in a lot of asteroids you see gravitational stratification. So in other words, the nickel and iron is heavy, and there was a body at some point that was large enough that the gravity was able to pull that nickel and iron towards the center, while the silicates, the lighter materials, remained on top. And so there's some indication of that. But again, I'm not the expert on asteroids. All right. Yeah. Okay, how big was the asteroid that caused the mass extinction of the dinosaurs? I don't know. I think I'm pulling numbers out of space here. Somewhere in the neighborhood of a kilometer. Anyone know? About a kilometer. It's very difficult to estimate because, it's the product of the mass times the velocity squared. That's how much energy you're putting into the system. And it's the energy that really is the biggest determination of what happens, how much energy you're putting in, you're hitting the Earth with. So a heavier object that was moving slower could do about the same amount of damage as a small object moving faster. Okay. Yeah.
What are the differences in speeds in the asteroid? Are we talking major orders of magnitude? Or?
What are the differences in speeds in the asteroids? Could be orders of magnitude. Again, I'm not certain. It depends on the two orbits, the orbit of the Earth and the orbit of the asteroid. And so I think that you can line them up so that the asteroid could hit very slowly, or could be hitting very hard. Did you have a comment on that, Kevin?
Asteroid speed velocity from 5 kilometers a second that are near Earth asteroids to as high as 25 kilometers a second.
So Kevin's a student at Maui College, and he's been working with asteroids. He's been working with the Phoenix telescope, and his comment was that he's seen asteroids, near-Earth objects, with speeds of 5 kilometers per second to 25 kilometers per second. And those are all things that are close by. All right?
You can look into that information on NASA's JPL Horizons website.
So yeah, if you want to search for NASA Horizons web interface, then you should come up with a very nice website that you can look at different asteroids by name and look at what their velocity towards and away from us is like, and where they are in the sky, a bunch of other great things.
Are there currently any imminent threats or possible threats?
Are there currently any imminent threats or possible threats? Yeah, there's one asteroid that has kind of hit the news a little bit lately. It's Apophis. And Apophis is a fairly sizable, I don't know the actual size, but it's big. And if we get hit by it, well, I don't know what's going to happen. But for a while they were saying it had a fairly high chance. Now they're saying it's maybe 1 out of 30,000, depending on the orbits. And in May of 2012, it's going to pass between the Earth and the Moon. So that's uncomfortably close. All right? And ironically, earlier tonight, I programmed the Phelps telescope to try and take some observations of this for Dr. Dave Tholen, who's one of the discoverers of Apophis. So hopefully we got Dr. Tholen's images, but they're trying to refine that orbit again. There are several objects that are potentially hazardous, but there's nothing that we're saying, yeah, it's big, it's going to hit us. There's nothing like that
So
that we know of.
when would it be predicted to hit if it were going to next year?
When would Apophis be predicted to hit if it were going to? I think it was 2069 was one of the, there were a couple of different dates. 2020. There were a few dates, but we yeah, it's coming. There are 2 or 3 times where it could intersect us and hit us, and so. But the predictions are pretty generally that we've got at least 20 years, at least more likely 40. Okay. Anyone else? All right. Well, thank you for coming. This concludes our broadcasting day.
Yeah.